Hi, this is Tim Shu from San Jose State University. I'm here to talk about optimization problems. So all throughout we'll be following a sort of motivating example, but I'll basically use that motivating example to illustrate the basic method that you can use to solve all optimization problems, or at least, it's as much of a guideline that I can give you for in general, because every problem, of course, is always different, because that's what makes problems interesting. Okay, so to our motivating example. So here's our motivating example. So suppose Nancy wants to build a wooden shelter for her dog. Something looks something like this. It's sort of got walls on three sides, on the top and the left and the right. And I've been teaching this stuff for 20 years. These problems are always the same. I mean, there must be some way to make this a little more interesting. So Nancy the puppy wants to build a wooden shelter for her pet human. She wants her shelter to be 3 feet deep and 50 cubic feet in volume. The shelter will have walls on three sides, on the top, on the left, and on the right. As you can see by the tablecloth here, our table is supposed to be the shelter, and the tablecloth represents the walls. So the question is, what height and width should Nancy choose for the shelter if she wants to minimize the amount of wood she uses for the walls? All right, so let's repeat that example again, perhaps in a slightly calmer fashion. So the idea is that Nancy the puppy wants to build a wooden shelter for her pet human, and it looks something like this. It has this it looks like, kind of a big wide staple. And the idea is that the shelter will have walls on three sides, on the top, on the left, and on the right. She wants her shelter to be 3 feet deep and 50 cubic feet in volume. So if you think of this as a big box, that big box should have a volume of 50 cubic feet. And the question is, what height and width should she choose for the shelter if she wants to minimize the amount of wood that she uses for those three walls? All right, so here's the basic method. This is the basic method that works for all optimization problems. In that, it doesn't really tell you how to do it. You can't really break it down to a cookbook. These are just general guidelines. Besides general methods for word problems, the most important of which I will repeat at the end, here's some specific steps that work for optimization problems. Step 1, name everything. Give a variable name for every quantity involved in the problem. 2, think really hard, and this is something that's very specific to optimization problems. What is it that you're trying to optimize? You want to figure out which of those quantities, and hopefully you gave a name for that quantity, most important quantity in the first step. Which of those quantities do we want to maximize or minimize? Third step, translate words and pictures to equations. Again, this is something you do for any word problem, but it's particularly important here. So what you want to do is you want to extract as many equations as you can from the statement of the problem. Step 4, after that, and this is something that's really unique to optimization problems. So what will often happen in optimization problems that you see in Calculus 1, in order to make them interesting, there will be different equations sort of floating around, and one of the equations will be the thing you want to maximize and minimize, and the other ones will be constraints. And so the idea is that you will is to use the constraint equations to reduce your problem to optimization in one variable. So again, often optimization problems will appear to have more than one variable, but they can be reduced to one variable by so-called constraint equations that appear in the problem. And step 5, oddly enough, even though this is a calculus class, this is the first step where calculus actually appears. Step 5, you use calculus. You find critical numbers, and you use the first or second derivative test, and you worry about the endpoints, and all to figure out where the absolute maxima and minima are. Hopefully there is one. I mean, if I, for example, as the instructor, give you a problem where there is no absolute maximum or minimum, that's sort of dirty pool. So hopefully there is actually some absolute maximum or minimum for your problem, and then you will find it using those usual calculus methods. So the most important thing, again, sort of a step 0 to all these steps, the important thing to remember is read the problem. As you can see in my other video about word problems in general, so many issues with word problems can be solved by reading the problem. Okay, so now let's return to our motivating example. So again, Nancy wants to build a wooden shelter with walls on three sides, and that shelter is going to be 3 feet deep and 50 cubic feet in volume. And so here's the height and here's the width. And the question is, which height and width minimize the amount of wood used in the three walls? So again, our 5 steps will be: step 1, we're going to name everything involved in the problem. Step 2, we're going to think, okay, what is it we're trying to optimize? Yes. Step 3, we're going to translate those words and pictures into equations. Step 4, we're going to use constraint equations to reduce the problem to one variable problem, as you'll see. Well, I hope you can sort of see here that there's sort of 2 variables, width and height, and we only know one variable calculus so far, so we have to use these constraints to reduce the problem to one variable problem. And step 5, whew, finally, we're going to be able to use calculus. All right, so tackling this problem in particular. So again, there's the problem again. So our first step is we're going to name everything. So what do we have? We have h, the height of the shelter. So let's call that h. I'm not very creative with my variable names, as you can see. Let's call the width of the shelter w. Let's call the depth of the shelter d. I know that d, the problem actually says d equals 3, but and you could actually skip this step when you get better at these things. But eventually, at this point, let's just say, okay, well, let's make d the depth of the shelter, and not worry about the fact that d is always equal to 3. And similarly, let v be the volume of the shelter. Remember, which is width times height times depth. That's the one thing you have to know, that the volume of a box is the product of its sort of 3 dimensions. And finally, let A be the area of the walls. Why the area of the walls? Well, we're using the area, I think this is a reasonable assumption to make. The area of the walls is going to be proportional to the amount of wood used. So really, the important, so when we say, spoiler alert for what's coming up next, when we say what height and width minimize the amount of wood in the walls, what we're really trying to do is minimize the area of those 3 walls. Okay, so here's our problem again. So, and now we're on to the next step, thinking hard. What are we trying to optimize? And like I just said, what we want to minimize, it says right here, we want to minimize the amount of wood in the walls, which really means that we want to minimize the area of those walls. In other words, we want to minimize A, the name we gave from the previous step. Okay, next step. So now, here we finally start to get some equations. Now we're going to translate all the words and pictures that we see over here into equations. So, for example, we're given that d equals 3. Remember, d was our name for the depth, and we're given that d is always equal to 3, and that v, the volume, is always equal to 50. Furthermore, as I was saying, this is the one sort of geometric formula that you need to know. You need to know that the volume of a box is equal to the product of its 3 dimensions. So here v is equal to w times h times d, and because d equals 3 from the previous step, we see that v equals 3wh. The area is a bit more complicated because there's sort of 3 pieces, so let's try to tackle these one at a time. So you do have to know the area of a rectangle is the product of its sort of 2 dimensions. So this top wall, this top rectangular wall, has area which is the depth times the width, which is 3w. And each side wall has area, each of these 2 side walls has area, the depth is here, times the height, which is dh, which is 3h. And so the total area of all 3 walls is the area of the top wall plus the area of the 2 side walls. So that's where this factor 2 comes from, because there's a left wall and a right wall. And so with a little algebra, this comes out to 3w plus 6h. All right, so now we sort of abandon the words. Now we just have numbers. Now, except we have to keep in mind that you're trying to minimize A. Okay, so now we know from before that v is equal to 3wh, which is equal to 50, and a is equal to 3w plus 6h. And here is the step where we use the constraint equations, and this is going to, as we're going to see, this is our constraint equation to reduce this function here to a function of one variable. So we're trying to minimize a, and we know that 3wh is equal to 50 is a constraint, because this sort of tells us that you're not completely unlimited in choosing what w and h are. The point is, if you pick a really wide table, it's not going to be as tall, because the volume is going to be 50 cubic feet. And similarly, if you pick a very short, a very tall table, then it's not going to be as wide. So that is our constraint. So we sort of arbitrarily choosing to get rid of the variable h, we can solve and get h equals 50 over 3w. So we're taking this and dividing both sides by 3w. And plugging that back into our formula for a, we see that a of w is, we're thinking of now a as just a function of just w, is equal to 3w plus 6 times 50 over 3w. So just plugging in this for h. And doing a little, well, not a little algebra, but really a little arithmetic. 6 times 50 is 3. 6 times 50 is 300, divided by 3 is 100. Yes, I can still do arithmetic. Excellent. And instead of writing over w, I'm going to write w to the minus 1, which, as we know, is a much more convenient form in which you can take the derivative with respect to w. So now this comes down to all comes down to minimizing a of w. A of w is equal to 3w plus 100w to the minus 1. All right, so finally, we get to the last step, the 5th step, using calculus. Phew! After all that stuff, it's just kind of a relief to use calculus, huh? Anyway, so we know from all the work we've done so far with word problems that a of w is equal to 3w plus 100w to the minus 1. And we also know, and the way we got there, remember, is by saying that h is equal to 50 over 3w. So here we go. How do you find the minima and maxima of a function? Well, you start with derivatives. So computing, we get a prime of w, taking the derivative of this with respect to w, is that a prime of w is equal to 3, because the derivative of 3w is 3. And the derivative of 100w to the minus 1 with respect to w is, well, remember, you take the exponent down front, and so we get minus 100 times w to the minus 2 because you subtract 1 from the exponent. So computing, we get a prime of w is equal to 3 minus 100w to the minus 2, which means that our critical number, well, actually what turns out to be our only critical number, w, is given by, well, how do you find critical numbers? You set a prime equal to 0, so we get 3 minus 100w to the minus 2 equals 0. So multiplying both sides by w squared, we get 3w squared minus 100 is equal to 0. Moving the 100 over to the other side, we get the 3, and dividing by 3, we get that w squared is equal to 100 over 3. And now taking the square root of both sides, we get that w is equal to 10 over the square root of 3. And remember, it's because w is a width, it's not going to be negative, and so we can ignore the negative square root. Yeah, so the only critical number of interest is that w is equal to 10 over the square root of 3. And note, I mean, just to be honest, I mean, morally speaking, you should keep going and not just sort of assume that, well, that's the answer at this stage. But it is often the case that if there is just a single critical number at this stage, it's often the correct answer. So, to be honest, you should think, okay, we're at least getting pretty close to the answer. But just to be morally correct about this, it's better to check and make sure, which we're going to do right here. So again, we know that a of w is equal to 3w plus 100w to the minus 1. And that h, the height, is equal to 50 over 3w. That was our constraint. And we're trying to check, is the minimal value of a achieved by taking w equals 10 over the square root of 3? Well, really the only sort of thing we have to worry about is what happens at the endpoints of the domain, really. And since w is always positive, the endpoints are really kind of w equals 0 and w equals goes to plus infinity. So we see by looking at this function, or you could just sort of graph it on a calculator or something, we see that as w approaches 0 or w approaches plus infinity, well, as w approaches 0, this term blows up to plus infinity and this goes to 0, so a will go to plus infinity. And as w goes to plus infinity, this term goes to plus infinity, this term goes to 0. So either way, a is going to go to plus infinity. So that if you have like if you think about it, an impossibly short shelter or an impossibly wide shelter, one of those surfaces, because the depth of each of those walls is always equal to 3, the total area of those walls is always going to go to infinity. And so so that being said, the point is that we can totally ignore these kind of possibly weird solutions. And so it must be the case that w equals 10 over the square root of 3 must be the global minimum for a of w. Oh yeah, but what were we asked? Remember, the original question that we were asked is to find the width and height that minimize the area. And so we also need to solve for the optimal height h. And so we do so as follows. Remember, so h is equal to 50 over 3w. It says it right there. And so this is 50 over 3 times the reciprocal of w, which is root 3 over 10. And so the 50 cancels out the 10 to leave a 5, and the 3 cancels out the square root of 3 to leave the square root of 3 in the bottom, and so h is equal to 5 over the square root of 3. So what did the question ask? The question asked, what height and width should Nancy choose in order to minimize the amount of wood used, or minimize the area? And we conclude that what Nancy should do is that she should build a shelter that is 5 over the square root of 3 feet high and 10 over the square root of 3 feet wide. Whew! Woo! We did it! All right, that's enough for now. Go do something useful. All right, here you go. Good puppy. Good puppy. Bye.